Hi, and welcome to Unit 5.2. This is Part 2. In Part 1, we utilize quantitative values Q and K to sort of determine or predict the direction a reaction will shift based on whether or not K was greater or less than Q. In this case, we're going to look at other changes, like changing the temperature or the pressure of a reaction, and how we can utilize our understanding of equilibrium to determine which direction or predict the direction the reaction will shift to reestablish equilibrium. Now, this principle is known as Le Shuttle EAs Principle, and it was developed by a guy with a very French-sounding name, Henri Louis Le Chatelier. And he says bonjour, by the way. He's a pretty shifty-looking guy in this picture, but if you think this guy is shifty, you should check out his principle. Ha, that was a joke. Okay, so going into Le Chatelier's principle, the Shuttle principle is used to make qualitative predictions about how reaction at equilibrium shifts to reestablish equilibrium in response to one of these three changes: addition of reactants or products, changing pressure, and one way to do that is by changing volume or changing temperature. So you make any of these changes, how will it reestablish equilibrium? And the reason why I underline the reestablish equilibrium is because before you made the change, the reaction was good. It was at equilibrium. And then you went around and you messed it up. So now it's going to have to shift to reestablish that equilibrium. Let's look at the first type of change, adding reactant or product. The key thing with the Chatelier's principle is basically any change you make on the system is going to want to counterbalance that change in order to get back to equilibrium. So let's take for the example of adding a reactant to your reaction. So once again, the reaction is good. This reaction here, let's say, for example, it's at equilibrium, it's good, it's happy, it's content. And then all of a sudden you're like, oh, let me add some N2 to this reaction, which is at equilibrium. Well, N2 is a reactant, right? You now have more reactant than you did when the reaction was at equilibrium. So which direction do you think the reaction is going to want to shift in order to reestablish equilibrium? All right, let's think about it. Right now you have too much reactant. You need to get rid of that reactant to get back to equilibrium. So in order to get rid of that reactant to get back to equilibrium, you want to shift toward the right, because when you shift to the right, you use up the reactants. So in the case when you add reactants, it's going to shift to the right. Let's say the reverse happens. Let's say you add product. Same sort of thinking will occur. If you add product to a reaction that's already at equilibrium, it's like now, whoa, I have too much product now. It needs to get rid of that product to get back to equilibrium. The only direction that will get rid of the product is to shift to the left, because when you shift to the left, you use up the product to make the reactants. All right, so let's take a look at this example. It says, which direction will the reaction shift above if you add 5 moles of NH3 to the reaction in a rigid vessel at equilibrium? So here we have this reaction here. If we add NH3, 5 moles of it, what's going to happen? Which direction will it shift? Well, NH3 is a product, so if we add NH3, our product, to the reaction, it's going to shift to the left. Now, I'm using the terms just adding reactant or product. You could also do the reverse, which is removing reactants or products. It does sort of the same sort of thing. If, for example, you removed N2 from the system was at equilibrium, then you took some N2 away. Now the system's like, hey, wait a second, I don't have enough reactant. I need to make more of it. And in that case, if you're removing reactant, it's going to shift to the right to make it. So it can either be add or remove. In your notes, you just have add, but the same thinking applies. All right, let's go into the next one now, which is change in pressure. So according to this principle, any change that you make, the system's going to counterbalance that change in order to reestablish equilibrium. So what happens if you increase the pressure on a reaction that's at equilibrium? What will the reaction do? The reaction will shift to decrease the pressure. So if you've increased the pressure on this system, it's like, oh, the pressure's too much. It's going to have to decrease it in order to reestablish it. And the key thing to remember about when you're changing pressure is that we're sort of using the ideal gas law to sort of think about what we're doing. The first thing we have to think about is how do we increase the pressure without changing temperature or the amount of reactant or product, because that was what we did previously. So there's one thing that we can do is we can change the volume. Remember that pressure and volume are inversely proportional. So that means that if you increase the volume, you would decrease the pressure, and vice versa. So now that if you're given a problem and you know that you've increased the volume, you know you've decreased the pressure, that's one thing that you kind of have to get from the ideal gas law in order to answer these questions. Once you know that, the other thing you kind of have to just consider, the other question you should consider is, okay, well, now that I know what happened to the pressure in the reaction, whether it increased or decreased, what must the reaction do to reduce or increase, depending on what your change was, to reestablish equilibrium without changing the temperature or the volume? So now you can't change temperature or volume. What else can you change? What's left is the moles. You can't change volume, you can't change temperature, you got to change the moles. So in this case, when we're focusing on the shift for pressure, we're going to focus on the moles. And you'll see that in the next example. So I just wanted to quickly go through like some of the ways, as we said before, for changing pressure. You can change it through volume. The other thing you can do is actually add or remove a gas involved in the reaction, but in that case, that's adding a reactant or product, and so you would use the rules that we saw for that. The other thing you do is add or remove an inert gas, and that's a gas that does not react or is not involved in reaction. And if you do that, there's actually has no effect on the pressure. So in your problems, you'll see problems where you're given the change in volume, or you're adding or removing an inert gas, and having to predict the change here. All right, so let's look at what happens. So the reaction is going to shift to counteract the change in pressure. So increasing the pressure, the reaction wants to shift. If you increase the pressure, the reaction wants to shift in the direction to decrease the pressure. And to do that, it's going to shift to the side with the least moles of gas to reduce the pressure. So, and you can tell that from the reaction. Like in this case, this has 4 moles of gas on the reactant side and 2 moles of gas on the product side. So for this reaction, if you increase the pressure and the reaction wants to reestablish equilibrium, it's got to shift to the product side because it has fewer moles, so that will reduce the pressure. On the flip side, if you decrease the pressure here, now the system has a lower pressure than it did at equilibrium, so it's going to shift to the side with the most moles of gas to increase the pressure. Okay, so let's take a look at this example. Which direction will the reaction shift if the volume of the container doubles or you add 5 moles of any gas? And you might want to just sort of think about what we talked about here. When we change the volume, that can tell us what's happening to the pressure, whether it increase or decrease. And if you add or remove an inert gas, that will have no change or no effect on the direction it will shift. Take a moment to read this and then see if you can figure it out. Okay, so the volume, if you increase the volume, that means that the pressure is going to decrease. And if the pressure is going to decrease, it's going to shift to the side with the most moles of gas to increase the pressure and reestablish equilibrium. In this case, for this reaction, it's going to shift to the right. On the other hand, if you add Ne is neon, it's an inert gas, it's not involved in the reaction, it's not reactive. And so this is actually going to have no change on the reaction. There will be no shifting. Okay, we looked at adding or removing reactants and products. We looked at pressure. Now let's talk about change in temperature. And for this, we want to think about exothermic and endothermic reaction. Remember, in an exothermic reaction, you release heat. So you sort of can think of heat as being a product. And for an endothermic reaction, you gain heat. So you sort of can think of heat as being a reactant. So that's kind of what I've written here. You might want to write this on that same slide. So with this in mind, if you, let's say, for example, you increase the temperature of your reaction. Well, if you increase the temperature of the reaction, what do you think will happen? Which direction is going to want to shift? Well, you increase the temperature, you sort of like think of it as increasing the heat. Which reaction gets rid of heat, uses heat up? The endothermic one. So it's going to shift in the direction of the endothermic one because, as you can see here, heat is sort of being consumed in this reaction. On the other hand, if you cool the reaction down, so you reduce the temperature, so that means you're like reducing the heat, and I'm saying that in air quotes here, you're reducing the heat, well, to reestablish equilibrium, it's going to have to increase the amount of heat, right? So which one produces heat? The exothermic, so it's going to shift in that direction. Okay, so again, increasing the temperature of the reaction is going to shift in the direction of whatever the endothermic reaction is. So when you increase the temperature, it shifts towards the endothermic. And when you decrease, it shifts in the direction of exothermic. What do I mean by that? If you look at this reaction above, they're giving you the balanced chemical equation and the delta H. Notice that the delta H is negative. So if delta H is negative, what is that, endo or exo? That's exothermic, and usually the delta H will be written for the forward reaction. So that means in this case, the forward reaction is exothermic. If we were asked which direction will the reaction shift if we decrease the temperature, so we have to think to ourselves, oh, if I decrease the temperature, it's going to want to shift in the direction of the exothermic reaction. Well, in this case, the exothermic reaction is the forward reaction, so it's going to shift to the right. Okay, so one quick note here is you also want to know that the fact that if the forward reaction is exothermic, like in our case, that means the reverse is endothermic. So just know that when you're solving. Because let's say, for example, they ask you which direction will shift if we increase the temperature. We would say, oh, increasing the temperature is going to shift in the direction of the endothermic reaction. When given this information, you look and you see you're given the delta H, it's negative. So that means the forward reaction is exothermic. So that means the reverse is endothermic. So if you increase the temperature, in this case, it would shift to the left because the direction of the endothermic reaction. All right, so now you have the CFU here. You're going to go through each of these and see, using your notes, predict the direction in which it will shift. So will it shift right or will it shift left based on the information? And when you press play again, the answer will be revealed. Okay, so Cl2 is removed. You're removing products, so it's going to want to shift right to reestablish equilibrium, increasing the product. Temperature decreases. If you decrease the temperature, it's going to shift in the direction of the exothermic, and here the reverse reaction is exothermic since the forward is endothermic, and we know the forward is endothermic because delta H is positive. The volume is increased. That means we decrease the pressure. So if you decrease the pressure, it's going to shift to the side with the most moles of gas to increase the pressure, and the side that has the most moles of gas is the product side, so it's going to shift to the right. If you add PCl3, which is one of our products, it's going to shift to the left to sort of counterbalance that. And if you add a catalyst, no change actually. There's no change with a catalyst, so that's something to remember. Okay, so that's it for this video. It's a quick little cartoon that I like. So if stress is applied to a system in a dynamic equilibrium, the system will adjust to relieve that stress. So de-stress like Le Chatelier. All right. Take a moment to sort of reflect and summarize what you've learned and submit any questions that you have for our next class. All right, take care. Have a quality day.